As we shall see, the semantics of first-order logic is based on the notion of a conceptualization of an application area in terms of objects, relations, and functions. The notion of an object is quite broad. Objects can be concrete, for example, the Eiffel Tower, Confucius, the sun, or they can be abstract, like the number 1, 2, 3, 4, the set of all integers, the concept of justice. Objects can be primitive or composite, for example, a circuit that consists of many subcircuits. Objects can even be fictional, such as a unicorn or Sherlock Holmes. In short, an object can be anything about which we want to say something. Not all knowledge representation tasks require that we consider all possible objects. In some cases, only those objects in a particular set are relevant. For example, number theorists usually are only concerned with the properties of numbers and are usually not concerned with physical objects, such as resistors and transistors. Electrical engineers usually are concerned with resistors and transistors and usually are not concerned with buildings and bridges. The set of objects about which knowledge is being expressed is often called a universe of discourse. Note that although in many real-world applications there are only finitely many elements in a universe of discourse, this need not always be the case. It's common in mathematics, for example, to consider the set of all integers, or the set of all real numbers, or the set of all n tuples of real numbers, as universes with infinitely many objects. Given a universe of discourse, a relation is a set of n tuples of objects in the universe of discourse, each set of which manifests a particular property or relationship. Suppose, for example, that we had a universe of discourse consisting of the numbers 1, 2, and 3. In this case, there are 9 pairs of numbers. Any subset of these pairs constitutes a binary relation. First, for example, here we have the less than relation. Second, we have some other random relation. We have the relation that's true of all combinations of objects. And we have the relation that's true of no combinations of objects. One thing that our definition for relations makes clear is that for a finite universe of discourse, there's an upper bound on the number of possible n-ary relations. In general, for a universe of discourse of size b, there are b to the n distinct n tuples. Every n-ary relation is a subset of these b to the n tuples. Therefore, an n-ary relation must be one of at most 2 to the b to the n possible sets. Sometimes in thinking about relations, it's helpful to visualize the tuples in different ways. For example, we can think of a relation as a table in which each row represents a distinct tuple. Alternatively, we can think about a relation as a graph in which the nodes represent objects and arcs represent tuples of objects. The notion of relation is an abstract one, not a particular encoding, and we can use whatever encoding makes most sense. Before moving on to functions, it's worthwhile for us to agree on some basic terminology. First of all, there's the notion of arity. The arity of a relation is the number of objects in each tuple in the relation. A relation of arity 1 has just one object per tuple. It's said to be unary. A binary relation has 2 objects per tuple. A ternary relation has 3 objects per tuple, and so forth. Every relation also has a cardinality. The cardinality of a relation is the number of tuples in the set. For example, the first relation shown here has cardinality 2, but arity 1. The second relation has arity 2, but cardinality 6. And the third has cardinality 3 and arity 3. A function is a special kind of relation among the objects in the universe of discourse. For each combination of n objects, called the arguments, a function associates a single object called the value. Note that there must be one and only one value for each combination of arguments. Functions that are not defined for all combinations of arguments are often called partial functions. And functions for which there can be more than one value for a given combination of arguments are often called multi-valued functions. By and large, we ignore partial and multi-value functions throughout this course. Mathematically, a function can be viewed as a set of tuples of objects, one for each combination of possible arguments, paired with the corresponding value. In other words, an n-ary function is a special case of an n+1-ary relation. For example, consider the unary function shown here can be viewed as a binary relation shown in the middle. In what follows, to emphasize the special property functions, we use a slight variation in our usual notation for relations, namely the use of an arrow in each tuple to emphasize the fact that the last element is the value of the function applied to the elements or elements before the arrow. Now, while every n-ary function can be viewed as an n+1-ary relation, we can see this, but not every n+1-ary relation is an n-ary function. We can see this by counting functions and comparing two relations. In general, for a universe of discourse of size b, there are b to the n distinct n tuples, and every one of these must assume one of b values. Hence, there are b to the n possible functions. By contrast, there are 2 to the b to the n+1-ary relations. In the case of a universe of size 4, there are 65,536 relations, but only 256 distinct functions.